Section: Introduction. In this section, we explore how large language models like ChatGPT are proficient in various tasks such as writing, coding, answering questions, and engaging in conversations. To enhance their abilities in different domains, fine-tuning specific to a domain has become crucial, but it can be costly. To address this, parameter-efficient fine-tuning (PEFT) methods like adapter weights, prompt weights, and LoRA have been introduced to reduce the number of trainable parameters. Among these, LoRA is widely used because it allows the adapter to merge back into the base model parameters. However, LoRA's performance in fine-tuning tasks has not consistently surpassed full parameter fine-tuning. It struggles on large datasets during continual pre-training, possibly due to its fewer trainable parameters compared to the base model, limiting its representation power. To tackle this limitation, we investigate LoRA's training statistics in each layer to bridge the gap between LoRA and full parameter fine-tuning. We observe that LoRA's layer-wise weight norms have a skewed distribution, with certain layers having more weights updated than others. This insight inspires us to sample layers based on their importance, leading to the development of Layerwise Importance Sampled AdamW (LISA) algorithm. LISA selectively updates essential LLM layers while keeping others unchanged, enabling training of large-scale models with less memory consumption compared to LoRA. When fine-tuned on tasks, LISA outperforms both LoRA and full-parameter fine-tuning approaches significantly, showing promise as an alternative to LoRA. Our contributions include discovering the skewed weight norm distribution across layers in LoRA and full-parameter fine-tuning, proposing the LISA algorithm for efficient large-scale LLM training, and demonstrating LISA's superior performance in fine-tuning tasks across different model sizes and tasks. Additionally, we discuss related work on large language models, the transformer architecture, models like BERT and GPT-2, and the shift towards more efficient training methods for LLMs, such as PEFT techniques like prompt learning, adapter methods, and selective methods. Section Summary. In this section, we introduce the challenges of fine-tuning large language models like ChatGPT due to the high cost associated with domain-specific fine-tuning methods. To address this, we propose the Layerwise Importance Sampled AdamW (LISA) algorithm, which selectively updates essential layers in large-scale models, enabling training with similar memory consumption as existing techniques like LoRA. LISA demonstrates superior performance in fine-tuning tasks, outperforming both LoRA and conventional full-parameter fine-tuning approaches by a significant margin across various model sizes and tasks. Section: Low-Rank Adaptation, LoRA. In this section, we explore the Low-Rank Adaptation, LoRA, technique, which is widely used in training large language models, LLMs. LoRA employs low-rank matrices to reduce the number of parameters, making computations faster and more memory efficient. One advantage of LoRA is its compatibility with models containing linear layers, where the decomposed low-rank matrices can be recombined into the original model without changing its structure. This allows for easy integration with other techniques like quantization or mixture of experts. However, LoRA may not always perform as well as full-parameter fine-tuning, especially in large-scale pre-training scenarios where full-parameter training is typically preferred. Apart from modifying model architectures, efforts have been made to enhance optimization algorithms for LLMs. Layerwise optimization, which involves optimizing layers sequentially, has shown benefits in training deep networks. Techniques like LARS and LAM have been proposed for large batch settings to improve generalization and prevent performance drops. Despite these advancements, optimization methods like ADAM and AdamW remain popular for LLM training. Some recent approaches, such as zeroth-order optimization and incorporating clipped second-order information for acceleration, have been explored to reduce training costs and speed up LLM training. To better understand how LoRA works with fewer parameters, we conducted empirical studies on various models, focusing on weight norms across different layers. We observed that in LoRA, certain layers like the embedding or language model head layers have significantly larger weight norms compared to intermediate layers. This emphasis on specific layers in LoRA may help capture language similarities efficiently but comes with limitations in representation power due to its low-rank nature. To address the limitations of LoRA's representation ability, we propose a method called Layerwise Importance Sampling AdamW, LISA. LISA aims to mimic LoRA's updating pattern by sampling layers to freeze during training. By adjusting the sampling probabilities based on weight norms, LISA can emulate LoRA's learning process while maintaining consistent learning rates across iterations. This approach helps bridge the gap between LoRA and full parameter tuning, allowing for a more efficient and effective training process. Section Summary. The Low-Rank Adaptation, LoRA, technique reduces trainable parameters by using low-rank matrices, making it compatible with linear layer models and allowing for efficient deployment without altering the model architecture. However, LoRA's performance may not always match full parameter fine-tuning, especially in large-scale pre-training scenarios. Despite this, LoRA variant methods with AdamW optimization remain prevalent for fine-tuning large LLMs, indicating the need for further performance enhancements. Section: Memory Efficiency. In this section, we wanted to show how memory-efficient LISA is compared to LoRA. To do this, we ran experiments to see how much GPU memory each method uses. We used a specific setup where we picked a random prompt from the Alpaca dataset and set a limit on the number of output tokens. We focused on two main settings: LoRA's rank and the number of activation layers in LISA. We kept the batch size the same for all models and used NVIDIA Ampere architecture GPUs with 80 GB memory. Looking at our results in the table, we found that LISA, especially when we added an embedding layer and 2 extra layers, used less GPU memory compared to LoRA when fine-tuning the Llama 2 to 70B model. Specifically, the LISA configuration with the embedding layer and 2 extra layers used only 75 GB of memory, while the LoRA configuration needed 79 GB. This memory efficiency was consistent across different model setups, showing that LISA's way of activating layers is better for saving memory. The reduced memory usage with LISA also made training faster. We saw a speedup of almost 2.9 times compared to full parameter tuning and about 1.5 times faster than LoRA. This speed improvement was partly because LISA doesn't introduce extra parameters like LoRA does. Additionally, the memory reduction from LISA led to faster forward propagation, highlighting the importance of efficient memory usage during training. We also tested LISA and LoRA on a fine-tuning task using the Alpaca GPT-4 dataset. LISA outperformed LoRA and full parameter tuning in tasks like writing, STEM, and humanities, showing its strength in tasks that require memorization. LoRA, on the other hand, was better suited for reasoning tasks. This demonstrates how LISA can be useful for various tasks while being memory efficient. Section Summary. In this section, we demonstrate the memory efficiency of LISA by comparing it to LoRA through peak GPU memory experiments. By optimizing LISA's configuration with additional layers, it significantly reduces GPU memory usage compared to LoRA, making high-quality fine-tuning feasible even on a laptop. This memory efficiency not only accelerates training speed but also enhances performance in various tasks, showcasing LISA's superiority over LoRA in domains like writing, STEM, and humanities. Section: Settings. In this section, we introduce additional tasks for fine-tuning our model on specific domains such as mathematics and medical question answering. We used the GSM-8K dataset for math, which has 7,473 training examples and 1,319 test examples, and the PubMed QA dataset for medical questions, which includes 211.3K training instances and 1K test instances. We evaluated our model on these datasets using different settings like 5-shot prompt for PubMed QA and chain of thought prompt for GSM-8K. We set hyperparameters like rank 256 for LoRA and E+H+4L for LISA, with more details in the appendix. Our results show that LISA consistently outperforms or matches LoRA in performance. In tasks involving following instructions, LISA performs better than full parameter training, making it a strong method for this scenario. Figure illustrates how LISA excels in writing, roleplay, and STEM compared to other methods. LISA also shows better performance than LoRA across all subtasks, demonstrating its effectiveness in various tasks. The comparison between LoRA and vanilla models in large models like 70B reveals that LoRA only slightly improves specific aspects, unlike expected. More fine-tuning experiments are detailed in the appendix. We conducted ablation studies to analyze the impact of key hyperparameters, such as the number of sampling layers and sampling period, on LISA's performance. Higher values for these parameters generally lead to better performance, but they also come with increased memory costs. Optimal values for these parameters enhance the model's performance up to a certain threshold, beyond which performance may decline. Overall, having more sampling layers and a higher sampling period tends to improve performance. We also investigated how stable LISA's performance is under different random seeds for layer selection. Our findings show that LISA's performance remains consistent across different runs, with a small performance gap, indicating its robustness. Additionally, we discussed the theoretical properties of LISA, highlighting its convergence guarantees and performance compared to other methods like LoRA. Section Summary. In this section, we introduce additional fine-tuning tasks in mathematics and medical question answering domains using the GSM-8K and PubMed-QA datasets, respectively. We evaluate the performance of LISA against LoRA, showing LISA consistently outperforms or matches LoRA across various tasks, especially excelling in writing, roleplay, and STEM aspects. Ablation studies on LISA's hyperparameters reveal that higher sampling layers and longer sampling periods lead to improved performance, with LISA demonstrating stability across different random seeds and theoretical convergence guarantees in optimization. Section: Better Importance Sampling Strategies. In this section, we consider better importance sampling strategies. We believe that the E plus H plus 2L and E plus H plus 4L strategies may not be the best because they randomly sample intermediate layers. We think that by considering the data sources and model architecture, we can improve the efficiency of the optimizer in the importance sampling process.